Most of the night sky is black. Most of the night sky is the space in between the stars. We're only interested in getting the light from the relevant bits, the star, the galaxy, whatever it might be.
So to do this, we need to get small mirrors into position deep inside the telescope. The big main mirror of the telescope still gathers all the light, and it brings it to a focus out to one side. It's a region called the focal plane. And the essence of all these different projects is to get these small mirrors into exactly the right position on the focal plane.
So we want to be able to pick up a large number of interesting objects at one time. And one of the ways of doing this is using robots to position the optics. One of the first prototypes we built was a pick and play system called Star Picker. It's a robot which just basically has an arm joint and an elbow joint, but that actually allows us to place a mirror on the focal plane in any number of different positions, just like putting places on a chessboard. So extremely accurate, just using two movements, an arm and an elbow, but it allows us to place the mirrors on this focal plane.
The next project was to build a system called CAMOS, where each of the small mirrors is permanently attached to the tip of a robotic arm.
And this allows us to position 24 mirrors, but using a slightly different robot technique. So in that technique, we have one joint, like an elbow joint, but then we actually have like a trombone movement, a linear movement.
CAMOS is now complete, and it has been installed on the Very Large Telescope in Chile. It will give us a different view on distant galaxies. We are now starting to look at new ways to tackle this mirror placement problem. We think it would be quicker and more efficient if we gave each mirror its own set of wheels so that it can drive itself into position. To do this, we now have to build a fleet of miniature robots.
In designing any robotics system, the three things to consider are power. How do we make the robot move? Then the drive system. How do we get that power to carry out the movement? We also need to know the position of the robot. The control software plays an essential role in this process.
It's an interesting part of the development of the work that we're trying to get the power from the floor. So rather than have batteries and things which would run out and we'd have to recharge, it'd be difficult, we take the power directly from the surface on which they run. But we've had quite a lot of fun of keeping the continuity, getting the power coming in all the time. So you can see that this robot isn't behaving very well. The other two, fine. We built these tiny little robots and they have very, very precise little motors, and the motor turns a wheel, and the motors are designed so they can take tiny little steps, and as they take a step it makes the wheel turn a step, and that means we get steps on the surface of the floor which are about a tenth of the width of a human hair. So it's an extremely precise system. We've written this bit of software and this allows us to talk to the robots, allows us to send them commands and check how they're behaving. So right now I'm just going to send them a little command so I can say, go forward 40,000 steps, and they should respond to that straight away, and off they go.
After the software is designed, we test it in a simulation mode where it pretends that it's controlling a robot. When that works, you combine the software and the hardware together. If it does behave as expected, then that's great. But because these are innovative new instruments, what tends to happen is something unexpected occurs, and you then have to think about how to go back, redesign the software to make it work in the way the robot behaves.
As we nudge the robot forwards, we see that we start to get, on the bottom here, a star starts appearing as we pick off a different bit of the sky, and slowly we can move that robot directly into position so that the star is right in the middle of the reflected light. This at the moment is purely sort of a research-based thing. It's not ready to go in a telescope tomorrow, it's not even ready to go in a telescope next year, but maybe in 10 years' time something like this might find its way into a real telescope.